Welcome everybody to this weekly series of CSIG talks, which happens at 10:30 a.m. on US Eastern on Thursdays. And we've had a few sessions on the IJCAI19 conference in Macau. So we had some people who spoke on a topic that was covered there. Last week we had the chair of the conference giving us a summary of what happened. And today we've got a couple of speakers from that conference. The first one is Lingfei Wu, who's going to talk about similarity preserving representation learning for time series clustering. I'm recording now. I'm going to hand over to him, and then we'll proceed. So I've stopped sharing. Lingfei, do you want to go ahead and share your screen?
Yeah, sure. Hello everyone. Let's first let me try to find where to share here. Okay. So should it be?
It's at the bottom.
Yes. Okay. Cool. Can you see my screen?
Excellent. Please proceed.
Okay. So thank you very much for the introduction and the invitation for give a talk here. So it's a great honor. And my name is Lingfei Wu from IBM Research. So today I'm going to talk about our work regarding how to learn representation or embedding for the time series clustering task. So this is joint work with Lei Qi, Jinfeng Yi, and Roman Vakani, and H. Dillon. So let me go to full screen. Okay, so it may have a little bit noise from my side because right now I'm in the MIT, but hopefully we will be okay. So regarding the time series, I don't know how many people have experience about time series, but time series have been extremely important in many. Any question?
No questions. Please go ahead.
Okay. So time series have been very important for many different areas. For example, in biology, energy, and finance, stock time series, and all these different applications. And so people have been working on this topic for a long time. Okay. So, but so far, so how to develop a very effective time series clustering technique still is an open problem. So there are many, machine clustering techniques that, the general goal is try to develop an effective, rebalanced, and efficient. And importantly, that is how easy to use that. So it's not really, easy to do the time series data in the sense that because time series is quite different from the common like data matrix in the sense that you may have this time scanning, shifting stuff. So how to deal with that? And sometimes the time series is often is not in the same length, in the sense that it's variable lengths. So how to deal with that is also very important for the time series representation learning. So the general goal here is try to learn the embedding, okay, through the representation learning techniques that we introduced in this paper. And so the target is that so you have a set of the time series. The T1 is represent one of the time series, and let's say you have n time series. And we try to find a mapping or learn a mapping so that we can transform each time series to its embedding space. Let's say embedding space, the dimension is D. Okay, so such that so we can satisfy the following condition. So S here is kind of a similarity function between that you can compute. And let's say STITJ is a similar function that between the similarity between two time series. And we try to find a vector representation for each of the time series. And then the inner product of that time series, the result can be used to approximate the similarity. Okay, so this is our general goal. So there are many time series measured so far in the literature. So like dynamic time warping, DTW, and they also have many new developed technique. So essentially, the DTW is well recognized as a golden standard for the time series distance measure because it's very elegant method, and have been shown that is considerably working better compared to the like Euclidean distance. But recently also have many new techniques developed, but essentially try to possess the same property as the DTW. So what's the DTW? Okay, so let's, I don't know, how many people know about DTW, so let's give a very quick review about DTW. So DTW have been one of the most common used, okay, for the time series similarity. So it's kind of edited distance in the sense that the symbolic string, but in the time series, so the dynamic time warping is one of the gold standard. So essentially try to, let's see, we have two time series. One is in the red shape, another one is in the red blue line. So we can see that, so the time series often have this like distortion or kind of scaling and shifting problem. So you want to align the corresponding data point in two time series in the sense that actually they should be match each other in order to measure the best distance between two time series. So if we use the Euclidean distance, you will see that it completely miss that. So one of the most simple example is that, so let's say you have a cosine signal, and you may generate the two cosine signal actually is exact same, but because that you can just shift them a little bit, then you can get a conclusion that these two time series have a larger distance, but actually it's not, because as you shift a little bit, they could be the distance could be zero. So that is more a very simple example. In the case we show in this slide, is more general form. So, but it gets at one point. So you have this temporal distortion. You have to use some sort of way to measure the correspondence between each of the time point. So the DTW is one of the thing. Is one of the distance measure that is perfectly to address this problem. So our work is built on this dynamic time warping. So the good thing, as I mentioned before, is that it behaves very well to deal with the temporal drift, and it's definitely better accuracy than the Euclidean norm. But the thing that, so the dynamic time warping is very, very expensive to compute. So it has at least a quadratic complexity compared to the length of the time series, and also is much less efficient. So how to accelerate that is become also very important problem. So essentially, as we mentioned before, we try to build like pairwise similarity matrix SI, try to measure the difference between two time series. And we try to find this embedding space that to transform the original time series to the embedded space such that it is the inner product that can approximate the original similarity value, right? So here is that you have aim of the time series, and you try to build this distance matrix use DW, for example. Okay, so conceptually that you can compute this distance matrix by force, right? And but essentially what we try to measure is really it's about similarity, not really about this distance. So we introduce this DW similarity, try to convert the DW distance become a DW similarity. Okay, but there are many ways to convert, but this is one way that we found that it's work generally quite well. So the intuition behind this transform is that, so essentially you can think about this kind of as a computer distance measure as we show here. So you can think about this is SIG we have defined is induced DW similarity, and here we have a similarity matrix S, and our goal is try to find a vector representation such as that the inner product that can approximate that, right? So basically, essentially, can also opposite as a treat as the opposite operation is that we try to factorize the similarity matrix S into a two vector representation. Here actually we assume you have a low rank. Why is low rank? We will explain later. And then you can use this low rank inner product to approximate the original time series. And this low rank inner product matrix X will be our embedding that can represent the time series. So if you're familiar with the clone method, you may feel that this is very similar to a clone method, right? So but essentially it's a little bit different because the way we construct the similarity is different. So why we assume that this is low rank? Because in theory, so when we do time series clustering, we already assume that the time series generated only from K cluster. So if this is a very minor assumption, and once it is certified that, so we can prove that so the final similarity matrix essentially is a low rank matrix. And because of that, so we try to seek a low rank embedding, such that the inner product of low rank embedding can use to approximate the original similarity matrix. And this is the theoretical motivation why we want to do that. However, in order to compute that, so that's another question. So do we really have to compute the whole similarity matrix? The answer is no, because that is not needed according to that if this the matrix itself is have a low rank. Okay, so that gives us a lot of opportunity to explore this low rank approximation technique by greatly reduce the computation. So one of the theory we can approve is that, so if the S is a low rank approximation, then the real element that we have compute to get this similarity matrix to factorize to our exact low rank embedding is n by n log n, in the sense that n is the number of the time series. So compared to the in order to compute this similarity matrix, it will be n squared, right? So we reduce this quadratic complexity into the linear complexity, and this will be enough for us to reconstruct this low rank approximation compared to that similarity matrix. And in order to do that, we also propose an efficient algorithm that essentially is exact cyclic collinear descent method try to solve this partially observed similarity matrix. When we say partially observed, means that we only compute part of the element, right? Because that is enough for us to do this matrix validation. So we use this exact coordinate because there's no need to choose a learning rate. Because this is exact, you will know that there's also have an inexact coordinate descent. But this is the advantage that why we choose the exact coordinate descent, and work very efficiently in practice, and we can have this theoretical guarantee of the convergence. We carry out some experiment, try to compare with the existing state-of-art method. So for example, K-shape, CLDS, and Gaussian kernel, and K-MEOD DW. So we perform experiment on the 85 UCR benchmark dataset. Okay, so here is a general average clustering performance compared to this state-of-art method. So we can see that we are definitely currently ranked number 1 in this category, and also we compare with each of the individual method use this kind of plot. So this plot means that in the x horizontal side is our method, spiral DW, and in the vertical side is the K-shape. Okay, this is one state-of-art method, and so if the dot point means for that particular data set, remember we have 85 data set, right? For that particular data set that we perform better than the K-shape or K-shape method, if it is in our method side. So the more data point you see here, that means that how many data sets that we perform better. So we can see that we are in many data sets we perform much better than the K-shape. And here is another example is a CLDS, we perform much better. And so that's all. So essentially in this work we present a very flexible approach, try to learn embedding from time series that have variable lengths. And we have a very efficient way to compute this low rank approximation through this low rank matrix completion theory approach. And also we show that with our method we can yield a very good clustering performance with a very simple clustering technique like K-mean. So this is all about this work. So we also have another time series embedding work that I'm the leading author for that paper. It's published in the AI State 2018. So in that where we introduce called the random wrapping series. So that is also another state-of-the-art method try to learn embedding from time series, but where we not only consider clustering, we also consider time series classification problem. And we also achieve a state-of-the-art performance there. So if you have interest, you can send me an email or can check the title of the paper and to look at the paper as well. So thank you very much. Any question?
Thank you, Ling Fei. Do you want to if you want your email, put it in the chat, in the Zoom chat?
Oh, sure, yeah.
Yeah.
So how do I put?
You can find it. I'm going